Hello students, in this video we'll begin our discussion of functions of a complex variable by recalling some basic properties of complex numbers, in particular thinking of the complex numbers as a copy of R2 with a certain field structure. So let's begin our discussion of functions of a complex variable. Let's recall complex numbers have the form z equals x plus iy, where I squared is -1. And of course, these complex numbers basically help us alleviate one of the fundamental problems of real numbers, right? So of course, I squared, so just a note, is that no real number A has the property that a squared is -1. So in particular, this number I over here is not a real number. It's a complex number. It's one of the imaginary units, right? So we call this the imaginary unit I, okay? And so what I want to do now is, we've seen complex numbers before in our study of differential equations. Formally, we say, okay, well, I can take 1 plus 3i and add it to 2 plus 4i, but let me think about this as sort of a copy of R2, right? And so now we can define, let's consider points in R2 xy with the following two operations. And for those of you, we'll eventually cover some abstract algebra, but of course these two operations basically give you like a ring structure, right? Or a field structure, two operations, okay? And so what are the two operations? So operation number one is xy, that's a point in R2, plus let's say zw. This will be as you expect it to be. Well, I'm going to make this x plus z, and then y plus w. This is what I call addition over here. And the second operation we'll define is xy times zw. And of course here, x, y, and z, so x, y, and z, x, y, z, and w are real numbers over here, right? So in other words, these things are all real numbers. Great. What will this be? Well, I'm just going to FOIL this out. This is going to be x times z, and then minus y times w, and then x times w plus y times z. Okay? You might say it's sort of a strange multiplication, but this multiplication exactly corresponds to what we know how we multiply complex numbers together, right? And so let's recall, so in other words, this thing over here is just an analog of saying, if I have a plus ib and c plus id, then we just FOIL this out, right? This will be ac, and then plus ibc, and then plus iad, and then plus I squared, of course, bd. And what do we know about I squared? We know I squared is equal to -1. So this is just ac, the a and the c, minus the b and the d, plus I times what? bc plus ad, okay? In other words, I just took what we know from, I call this like the pre-calculus version of complex numbers, and put it into this more formal structure over here, right? And so these two operations give me a way of thinking of, these give me two operations on points in R2 that exactly corresponds to ordinary addition and ordinary multiplication of complex numbers, right? And so that helps us to understand the geometry of complex numbers as well, because I'm really thinking of the complex numbers as a point in R2, right? So one complex dimension is really two real dimensions. Excellent. Okay. So remark about these things. So remark. The point 0, 0 is the additive inverse, is the additive element, additive identity element. And 1, 0 is the multiplicative identity. Excellent. And that's easy to check, right? Because I plugged in if, for example, we took this equation over here and we plugged in a 1 and then a 0 over here, what happened? I replace all the z's with what? I replace all the z's with 1, all the w's with 0. So those should be in what? That'll be turned into an x. That's going to turn into a y, right? So in other words, that is clearly an element. If I plug in 0, 0 over here, then what's going to happen over here? This is going to turn into an x comma y, and we see that 0, 0 is the additive element, identity element, and then the 1, 0 is the multiplicative identity element. Great. All right, so now here's the question. So with this structure, how do you find the inverse, right? So question, what is the inverse? Multiplicative inverse point xy, which is not 0, 0. Okay, how did you figure this out? Well, what do I want? I would like x times y times a point z times w to be the identity, right? And the identity we know is 1, 0, 1, 0. And so what's that going to correspond to? That's two equations, two unknowns. Of course, over here, I'm assuming that xy is fixed, right? So here, xy is fixed. Beautiful. All right, and so if that's the case, what do we have over here? We're going to have x times z minus y times w is equal to 1. That's the first entry. The second equation we're going to have over here, if we're going to have y times z, and then plus x times w is equal to 0. Beautiful. That's two equations, two unknowns. It's a 2x2 system. And so we can find out using Cramer's rule what the solution to this system is, right? So the solution to this system over here is exactly what? So what's z going to be? So the z is going to be the determinants by Cramer's rule of what? Of 1, 0, and then negative yx over the determinants of xy, negative y, and then x, okay? And what's w going to be? W is going to be the determinants of xy, and then what? Then I'm going to have a 1, 0 over here over the same determinant, x, negative y, x, okay? And so this top determinant here is just going to be x over x squared plus y squared. And this w over here is going to be negative y over x squared plus y squared, okay? So in other words, that's the multiplicative inverse. And so the inverse, therefore, the inverse has the form what? The inverse has the form x over x squared plus y squared, and then negative y over x squared plus y squared. Later on, when we start to study these functions over here, this is my u and this is my v, we're going to see that both those functions are harmonic functions. They satisfy the Laplace equation. And so we get a very wide class of solutions to the Laplace equation by looking at certain sort of analytic functions that are real and imaginary parts. Beautiful. Now, of course, you might say, well, wait a minute, this looks very familiar to me, and it should be very familiar to you, because if I look at 1 over x plus iy, what was the trick to do this? The trick to do this was to multiply this by 1 over x minus iy, which we'll discuss in further videos. I'm going to discuss real and imaginary parts, because this is really the conjugate of that point. So we sort of recall this is what we started to do when we took pre-calculus, right? And so what we did is, okay, well now, and then on top what goes, on top, we have to multiply by the same thing, right? You want to multiply by 1, right? So this is going to be x minus iy. So the top is just going to be x minus iy, and the bottom is going to be what? It's going to be x squared, and then plus what? Plus, then I have an I and an I with a negative sign, so it's going to be a plus x squared, and then an iyx, and then a negative iyx, and so that's going to be 0. So this exactly is what? This exactly is x minus iy over x squared plus y squared. Now, what is the first entry of this thing? If we're thinking of the part without an I as the first entry, that's going to be what? That's going to be x over x squared plus y squared. And the second entry over here is going to be what? It's going to be negative y over x squared plus y squared, right? So in other words, what we've done over here is this is sometimes referred to as identification. We have identified identification of R2 and C. And how I've identified them, I've identified R2 and C with this multiplicative structure. Now, what this allows me to do is this allows me to sort of think about problems. I can sort of lean on what now? I can lean on problems and tools in real analysis, which we have a whole bunch of material on already. So I can use tools from real analysis like Cauchy sequences, the Weierstrass M-test. I can use inequalities from real analysis to learn about complex numbers, right? So a lot of the complex analysis we're going to be learning is going to be heavily contingent upon the real analysis. And the beautiful thing that happens, as we're going to see, as I alluded to earlier, is that these terms over here, these components of the real and imaginary part, are harmonic functions. They satisfy the Laplace equation. And we've talked about the Laplace equation a great deal throughout the course of these videos. And we're going to see in further videos how we can basically extend complex function theory and harmonic function theory. And it's really just a tremendously beautiful subject that appears. And so this identification, while relatively straightforward, gives us sort of a good sort of base level hint as to what the connection is between real analysis, complex analysis, and harmonic function theory. Thank you very much.